All right. So, namaste and a warm welcome to lecture 1 of computational topology. So, the lecture that we had on Tuesday was more introductory in nature. So, we will refer to that as lecture 0. And starting from today, our formal lectures will begin, and hence we will refer to this lecture as lecture 1. All right. So, all my lecture notes, okay, will be available in Microsoft Teams. In particular, there will be two versions. One is the version which I will refer to as unannotated, and then there will be a second version which will be annotated, which will include all the remarks that I will add to these lecture notes during the live lecture. Okay, so both these lecture notes will be available via Teams. However, the unannotated one will be available before the lecture itself. So in fact, if you go to your class notebook in Microsoft Teams, if you sort of look carefully, you will see like a table in which the details of every lecture will be provided. So in particular, if you look at the details corresponding to lecture 1, there you will see a link to the lecture notes that I am going to use for today's class. Alternatively, you can go to the file section in the general channel, and if you sort of look around, you will find a folder titled class material, and in that as well you will be able to find these lecture notes. Okay, so those who want to sort of use those lecture notes in parallel, they are more than welcome to use them. Is that okay? All right, so with this, maybe we can begin. So as I mentioned in the previous class, if you have any questions, I encourage you to raise your hand. So when I've finished, discussing the thought that we were discussing at that point, okay, I'll request you to unmute, and then you can go ahead and ask questions. All right. Okay, so in the previous class, we sort of saw like an overview of the whole course. Okay, so today we will begin with the specifics. Okay, so and of course it will touch a bit upon the things that we discussed in the previous class as well. Okay, so this course is titled Computational Topology. Okay, so in a sense, computational topology is a subset or a topic that is complementary to this bigger topic called as algebraic topology. Okay, so the fundamental problem in topology or algebraic topology is to check if two spaces are homeomorphic or not. Okay, by homeomorphic, I mean loosely, homeomorphic means that if the two spaces are one and the same, right? So symbolically, we will write this question in the following way. So let's say we have been given these two spaces. One is denoted X and the other space is denoted Y, right? And we are interested in knowing if X and Y are homeomorphic. Okay, so the symbol over here, whenever I write such a symbol, I mean homeomorphic. Is this okay? So here is an example for such a question. So let's say the first space, that is X, is the real line, right? So I'm sure everyone has seen the real line. So the arrows over here indicate that this line sort of extends forever in both the direction. And let's say there is another space which is Y, which is S1. Okay, so S1 refers to this circle over here, and the interior is hollow. Okay, so let me emphasize that the interior is hollow. Okay. Um, Another way to look at S1 is the following, that it is the boundary of the solid disk. Okay, so you know the solid disk, right? So you draw this solid disk and you take the boundary of this solid disk, whatever that is. Okay, so that is what is S1. Okay, all right. So the question that we are asking is whether this space over here and this space over here, are they homeomorphic or not? Okay, so homeomorphic is a technical term. Okay, if you haven't heard of homeomorphism before, it's fine. You can, for the time being, think of the question as asking whether these two spaces are one and the same, right? So in the previous class, I sort of gave a formal definition of what homeomorphism means, right? So so what homeomorphic means? Okay, so two spaces are said to be homeomorphic, right? So X and Y are said to be homeomorphic if there is a function f that goes from X to Y, right? So if there is a function f that goes from x to y and satisfies the following three properties. Okay, so what are these three properties? We require that f be continuous. We require that f be a bijection. That is, it should both be one to one and onto. And the third thing that we require is that the f function should have a continuous inverse. Okay, so the fact that f is a bijection automatically implies that it has an inverse, but we also require that its inverse be continuous, right? So whenever there is a function f from x to y which satisfies these three properties, then we will say f is an homeomorphism. So the map is referred to as a homeomorphism. Okay, and x and y would be said to be homeomorphic. X and y are homeomorphic, right? And in symbols, I will say something like this. Is this okay? So in order to verify if these two spaces in the example, that is x and y, whether they are homeomorphic or not, okay, one would need to check whether such a function exists or not, right? So in general, to verify whether such a function exists or not is quite hard. Okay, so I hope the context is clear. The goal is to check if two spaces are one and the same, right? More formally, whether they are homeomorphic. And in order to answer this question, one has to verify the existence or non-existence of a function or a homeomorphism or a function that satisfies these three properties. However, this in general is hard, right? So a standard alternative is to try to find a topological property, right? A property concerning topology that is invariant. Okay, so this is a very, very important word. So that is invariant under homeomorphisms. Okay, so that is invariant under homeomorphisms. Okay, so we try to find a topological property that is invariant under homeomorphism, that is satisfied by one space but not satisfied by the other, right? So let me just explain what do I mean, right? So let's say x and y, okay, were indeed homeomorphic, right? So we try to find the property P of this space, okay, which is retained under homeomorphism. That is, if you sort of ask this property, under image F, right? So F is the homeomorphism, and we ask, is the same property, would it hold under Y, right? Or would it hold for Y as well, right? So if there is a property that indeed is invariant under homeomorphism, then one would expect that if X and Y are homeomorphic and there is a property P that is true of X, then that same property should also hold for Y, right? So we try to find such a property, and in case we manage to show or identify a property, right, which is true for X but not true for Y, then one can conclude that X and Y are not homeomorphic. Okay, so let's look at that earlier example, right? So again, the question is, we have these two spaces R and S1, and we are interested in knowing whether R and S1 are homeomorphic or not. Okay, so the goal is to try and identify a property that is preserved under homeomorphism, right? So for the sake of contradiction, we will assume that this space and this space are indeed homeomorphic, right? So this means that there is a function f that goes from x to y. So what does this part mean? It means that if you give an element in x, so let's say little x, okay, so f of x, okay, f of x will be an element in y. So you can see this depicted pictorially over here. So whatever x you give me, I will give you some f of x that is on the circle. Is this okay? And we are, for the sake of contradiction, we are assuming that these two spaces are indeed homeomorphic, right? Which means that if I find a property that is preserved under homeomorphism, then if that property holds true for this space, it should also hold true for this space, right? However, as we will see now, okay, there is a property which is true for this but not true for this. So what is that property? So let's say we pick some arbitrary but fixed x, right, and we try deleting that point, right? So what will happen if I delete that point? I hope you agree that there will be like a puncture that will be created over here, right? So because of this puncture, this space will get divided into two components, or this space would get disconnected. On the other hand, whatever was this mapping, wherever f of x turns out to be, if I delete that specific point, then you can see that the resultant will have only one component, right? It doesn't get disconnected. Is this okay? So since f is arbitrary, so what we are claiming is that whatever be the homeomorphism, wherever this x is mapped to on this circle, if I delete x here, I get two disconnected components. On the other hand, if I delete f of x here, I only have this single component. Okay, so you can see that we have identified a property, right? So why this property is preserved under homeomorphism, that is a question I'm not answering, right? This is a question for a more mathematical course, but for the time being, you can believe me that if I sort of remove a point and I look at the number of components in the resultant object, okay, that should be preserved under homeomorphism. So this is a property that is preserved under homeomorphism, and I'm showing that if I perform this operation on the left, then I get a different answer. And if I perform the same operation on the right, I'm getting a different answer. Okay, so that is why these two spaces are not homeomorphic. Is this okay? So what have I done? I have identified a property that ideally should be preserved under homeomorphism, but I showed that that property is not preserved with respect to these two spaces, whatever be this homeomorphism. Is this okay? And consequently, I managed to conclude that R and S1 are not homeomorphic. Is this okay? That means the real line and the circle do not have the same shape. That's what I managed to conclude, right? So the issue with this approach that I suggested above is that such elementary ideas, right, like deleting points and doing some simple operations like this are not very effective. Okay, so they are not very effective in general scenarios. Right. So what is the alternative? Well, the alternative is to come up with some sophisticated topological invariants. Okay, so this word is something important. So an invariant, okay, so an invariant is a property that is preserved under homeomorphisms, right? Which means that if two objects are indeed homeomorphic, then this property, if it is satisfied by one space, we require that the homeomorphic space should also satisfy the same property, right? So what we have managed to identify so far is that identifying this elementary properties, okay, by trial and error, may be quite hard, right? So in general, we require some sophisticated topological invariants, right? And the field of algebraic topology. So if you sort of wanted a one-line summary of what this field of algebraic topology was all about, well, it's a study of attempts by some of the greatest mathematicians of recent times, such as Euler, Riemann, Betti, Poincaré, and others, right, to identify and study and construct such topological invariants. Okay, so this is like a two-page overview of what algebraic topology is. So what's the summary? In algebraic topology, we are interested in knowing if two spaces are homeomorphic or not, right? Simple operations or simple properties are difficult to identify, in which one can easily say, okay, this is satisfied by this space and this is not satisfied by that space. Okay, so such properties are very difficult to identify, right? And the alternative is to identify some sophisticated topological invariants. Okay, so that's what this field of algebraic topology is all about. Right. So indeed, if you sort of take a course on algebraic topology, you will see that there are several topological invariants. Okay. However, the issue with most of these topological invariants that they are not computational friendly, right? So they are not easy to compute. Okay. So that's the reason most of these topological invariants are not of interest to us. Okay, when I say us, I mean people who are more interested in doing some computational analysis with these objects. Okay, so they are not very computational friendly, right? An exception, however, to this statement over here is that of homology groups. Okay, and this in some sense will form the focus of the first half of the course. Okay, so I hope this is clear. So the course is titled Computational Topology. In some sense, we are interested in identifying topological invariants that are easy to compute, that are more computation friendly. Okay, and an example of such a topological invariant is what are called as homology groups. Okay, and this is what will form the focus of the first half of this class. Okay, so let me pause here for a couple of seconds. If you have any questions with regards to what we have seen so far, this may be a good time to ask. Do you have any questions? Yes, Deep, go ahead.
Yeah, I just want to confirm that when you, the exception meaning that for computation, homology groups are relatively easier when it comes to the computation aspect. That's what you meant.
That's right. That's right.
Okay.
So there are other topological invariants like fundamental groups and so on and so forth. Okay. However, they are not very computation friendly. Is that okay?
Yeah. Okay.
Okay. Are there any more questions? Okay. So I don't see any raised hands. Yes, Rankit, go ahead. Do you have a question?
Yes, sir. The example you gave of proving that the real line is not homomorphic to the circle, can you suggest some one or two more properties, topological properties, which prove the same?
Which prove the same, right?
Yeah.
So, okay, I'm not able to think of something immediately, right? Maybe if I'm able to think of it, I'll post it later on Teams. Is that okay?
Sure, sir.
Okay. All right. Okay. So, okay. So as I mentioned, the summary is that that we are interested in topological invariants that are computation friendly, and an example of that is homology groups, right? So some of you must have seen groups. Okay, even if you have not seen groups, in the next class we will go over some basic ideas of groups and so on and so forth, right? So so these homology groups are basically groups, right? So these are groups, and to every space X, right, we will assign a sequence of such groups, right? So we will assign a sequence of such groups. Okay, and in particular, what do I mean is that I will assign hk of x for k bigger than equal to or maybe I'll say I will assign k in the set of integers. Okay, so for every k which is an integer, I will have a corresponding group, right? So if you say, let's say k is let's say 3, then I will have h3 of x. So this is a group that is attached with this space x, right? Similarly, if you have k equals -1, I will have h -1 of x, and similarly, if you have k equals 100, I have h100 of x. Is this okay? So I have a sequence of groups that are attached to this space x, right? And we will refer to hk of x, okay, as the kth homology group. Okay, so what these groups are, how to construct them, and so on and so forth. Okay, we will discuss this in the next class. However, for the time being, you need to understand that when I say homology, I basically mean the sequence of groups that are associated to a given space X, right? And the key thing is that these homology groups are invariant under homeomorphisms, right? So what do I mean by that? For homeomorphic spaces, homology groups are isomorphic, right? So this is loosely saying that the homology groups are one and the same. However, in the context of vector spaces, for example, you already know that, to understand when two vector spaces are one and the same, right? It's not just to say that, they have the same objects, right? What we instead require is that the operations that we define on these vector spaces, okay, they behave similarly, right? So to give you an example, let's say you look at the vector space of n cross n matrices, right? And let's say you look at the vector space Rn square, right? So this vector space basically includes all vectors of size n square, right? And this is a vector space whose elements are n cross n matrices, right? So as the objects in these vector spaces are different. In one, it's a vector, right, of length n square, and in the other you have a matrix of size n cross n. Nevertheless, one can show that this vector space and this vector space over here are isomorphic, because if you sort of define an addition operation and a scalar multiplication operation on the left, and if you define an addition operation and scalar multiplication operation on the right, okay, then one can show that under these two operations, the behavior of these vector spaces is one and the same, right? So consequently, these two vector spaces, instead of saying they are same, we say that they are isomorphic, right? So in the same sense, one cannot, I mean, saying that two groups are the exactly one and the same, that is too restrictive a statement. Okay, we want to sort of look at it from a more general perspective. When two groups are similar, okay, and the formal word is isomorphic, right? So the way to understand what I'm saying over here is that when two spaces are homeomorphic, their homology groups are similar, and formally we can say that their homology groups are isomorphic. Okay, so when we look at groups, when we study groups in the next class, indeed we will understand in a bit more depth what do I mean by isomorphism of groups and so on and so forth, right? So in this sense, these homology groups are invariant. They are preserved under homeomorphism. Okay, so that's the most important part, and why these homology groups are important. However, you also need to keep in mind that the converse is not true. Converse is not true means the following. Let's say x and y, okay, are two spaces, and let's say hk of x is isomorphic to hk of y, okay, for all k. So let's say you manage to show that every homology group that is associated with x is isomorphic to every or the corresponding homology group associated with y. This does not imply that x and y are homeomorphic, right? So the implication is only one way. Homeomorphism implies the homology groups are isomorphic. However, the converse is not true. By that I mean, even if the homology groups are isomorphic, that does not imply that the two spaces are homeomorphic to each other. So one can immediately ask, oh, if the converse is not true, how are these homology groups useful? The homology groups are useful in the following way, right? So they are useful in the following way, right? So what does this say? Suppose you manage to show that for the given two spaces x and y, that some of the homology groups are not isomorphic, right? Suppose you manage to show that for the given two spaces x and y, their homology groups are not one and the same, right? And one can then indeed conclude that they definitely must not be homeomorphic, right? So one of you, Rankit, actually asked me, can we suggest one more topological invariant by which one can show that these two spaces are not one and the same? Well, the immediate answer is one can look at the homology of this space, and one can look at the homology of this space and show that they are different, and consequently they are not homomorphic. Okay, so here is an answer. I mean, here is the specific detail. If you sort of ask how many circles or how many holes of dimension 2 are present in this space, okay, so of course you don't know what a hole means and so on, but intuitively it's a hollow region of dimension 2. So in this case, there are no holes, okay, of dimension 2, whereas here on the figure in the right, you can see that there is a hole here, okay, because this circle is hollow. Okay, so this hole is hollow. I mean, this is a sort of hole of dimension 2, right? So the number of holes of dimension 2 over here is 1, right? So this is at a level of intuition. However, in subsequent classes, you will see how to formally count these holes, what these holes mean, and so on and so forth, right? But for the time being, you can see that the homology of this space and the homology of this space are not one and the same, and based on that, again, one can conclude that this space and this space are not homeomorphic. Is this okay? So the bottom line is that homeomorphism implies that the homology groups are isomorphic. However, the converse is not true. Nevertheless, the use of homology groups is that, by showing that x and y do not have not all of their homology groups are isomorphic. Using this, one can conclude that x and y are not homeomorphic. Okay, Agnit, can you go ahead and ask your question?
I was just saying that compactness is another property that doesn't hold there.
That is true. Okay, thanks for reminding me that. Okay, so compactness is another property with which one can show that, that is a property that is preserved under homeomorphism, right? And one can see that the real line is not compact. However, this S1 space is compact. Yes, Ayush, go ahead.
So how is K negative in the upper part which you just showed? How can K be negative there? Yeah, yeah, the Kth homology group.
So the intuitively you're thinking of what could be a negative dimensional hole. Is that your question?
Yeah.
Okay, so once we define this formally, you will see that we can define this for all integers K. Okay, so please wait for the formal definition. It will become clear. Is that okay?
Okay, sir.
All right. All right. Okay. So I hope so far the overview is clear. Algebraic topology is the study of topological invariants. A special category of that is these homology groups. They are interesting to us as computer scientists because they are computation friendly. Right. However, the key thing you need to notice that homeomorphic spaces, imply that the homology groups are isomorphic. However, the converse is not true. Right. Okay, so while homology groups can be studied for generic spaces like real lines or Euclidean spaces, okay, these different manifolds and so on and so forth. Okay, so while one can indeed study homology groups for these generic spaces, our focus in this course will be on the homology groups associated with what are called as simplicial complexes. Okay, so this will be the focus of this course, to study homology groups of simplicial complexes. Is this okay? All right. So given this, one immediate question that may arise in your mind is, okay, now what the hell is this simplicial complex? Okay, so let me now try and define that. Okay. So the rest of today's class will be devoted towards understanding what a simplicial complex is and some of its properties, some of the definitions associated with the simplicial complex that we will be regularly using, and also some notion of geometric realization. Okay, so when I reach that part, I will explain what this concept means. All right, so let's begin by understanding what a simplicial complex is. In particular, we will be studying the concept called as an abstract simplicial complex. Okay, so an immediate question that may arise perhaps in your mind is, okay, what is now abstract? Okay, so the before explaining what abstract is, let me tell you something analogous, which is also an abstract entity. Okay, so a vector space, or for example a group. So if you ask me what is the vector space or what is the group, right, there is no physical meaning to that. It's just a purely mathematical construction. Right. So in the same way, when I mean the definition of simplicial complex that you will see now, you will see that it's a purely mathematical construction by itself. Okay, there is no physical meaning that is attached to it. Okay, that's why we say that what we are going to define now is referred to as an abstract simplicial complex. Okay, however, later on in the course, we will be sloppy and we will stop saying that it's an abstract simplicial complex and so on and so forth. I will either say it's a simplicial complex, or I'll be even a bit more lazy and just call this as a complex. Okay, this is just for convenience. I don't want to repeatedly say abstract simplicial complex, abstract simplicial complex. All right. Okay, so let's now look at the formal definition of what an abstract simplicial complex is. Okay, so typically we will denote such an abstract simplicial complex by this notation, capital delta. Okay, so this is delta. So what is delta? It's a collection of non-empty subsets. Okay, that's the first thing. It's a collection of non-empty subsets. However, the key thing is that this collection should satisfy an important property. And what is that property? That this collection must be closed under the subset operation. Okay, so let's formally look at what does this property mean. Okay, so we have been given a collection of subsets. Let's say A is an element of this collection. So A itself is a non-empty subset. And let's say B is another subset, right? Or B is another set, which is a non-empty subset of A. Right, so A belongs to delta and B is a non-empty subset of A, right? So A belongs to delta and B is a subset of A, and we know that B is non-empty. So for this delta to be a simplicial complex, we necessarily require that B also belongs to this collection delta. Okay, so notice that every subset of A should also lie in delta, and that is what this property over here means, that it should be closed under the subset operation, right? So one note over here, delta is a purely combinatorial object in nature. Okay, so this is a purely combinatorial object in nature. Okay, so that is in this definition. Okay, there are no geometric notions attached. There are no, we don't care about the different orderings and so on and so forth. Okay, it's a definition in terms of sets. And if you recall, in sets, we don't care about orderings. And in this definition, there is no geometry also attached. Okay, so it's a purely combinatorial object. Okay, so let me pause here for a second or two. If there are any questions with this definition, okay, this may be a good time to ask. In any case, I have a bunch of examples soon, and it may become even clearer what this simplicial complex means. Yes, Jayant, go ahead.
Hello, sir. So here subset is what kinds of sets, like subset of these sets?
So at this point, it's a collection of, so maybe there is some universal space and we look at subsets of that, and it's a collection of subsets of some universal space. Okay, so it's a collection of sets, right? And we are given a collection of sets and we require that this property be satisfied. Okay, typically, what we will have access to is we have some vertex set V, right? And we may look at non-empty subsets of this vertex set V, right? Non-empty subsets of V. Okay, this is how typically we will look at it. All right. Okay, so as I mentioned in the previous class, simplicial complexes are useful to model higher order relations, right? Unlike a graph which can only model binary relations, right? So let me just give you an example. Okay, so let's say the vertex set V is made up of 3 vertices, 1, 2, 3, right? So when you must have studied about graph, you must have seen that to define a graph, I need to specify the vertex set and the edge set, right? So for example, the vertex set could be this V over here, and the edge set could be, let's say, 1, 2, and maybe 1, 3. That's it, right? So this is how this graph we can pictorially represent, right? So this is the graph which has 3 vertices, right? And these 2 edges, right? So I will request you to ponder whether one can view a graph also as a simplicial complex, right? So I can ask you whether you can think of graph itself as a collection of subsets and whether it satisfies the closed under subset property or not. Okay, so I will ask you to think about it, and maybe later on we can discuss this a bit more, whether you can view this graph as a simplicial complex or not. Okay, so at this point, this is just a different way of writing or denoting a graph, and often this notation is used in this fashion just for convenience, so that it is clear what a vertex set and what a edge set is, right? Whereas in a simplicial complex, we may not explicitly identify what the vertex set is, what this is. Instead, we may just give you the collection of all possible subsets that together define this simplicial complex. All right. Okay, so as I mentioned, a graph is useful to define these binary relations. So you can see that there is a relation between 1 and 3, which is made up of only 2 entities. Similarly, here there is 1 and 2, so there is a relation between just 2 entities. So a graph is useful to sort of model relationships which are binary in nature. However, simplicial complexes, as we will see, are useful when higher order relations are also needed or of interest. Another entity, okay, which also is useful for modeling higher order relations, is that of a hypergraph, right? So one can immediately ask, what is the difference between a simplicial complex and an hypergraph? Okay, so let's look at the formal definition of a hypergraph. So a hypergraph again is denoted by a pair V comma E, right? Just like a graph. Okay, however, the difference between a hypergraph and a graph is that here V as before is a vertex set. However, E is a subset of So E I should write it in this fashion. E is a collection of non-empty subsets of V, right? So E is a collection of non-empty subsets of V, right? And these elements of E are referred to as hyperedges, right? So now let's ask, what is the difference between a hypergraph and a graph? Well, the difference is that notice that the elements of E, okay, are sets of size 2, right? So this is a set of size 2. It has only 2 elements. Similarly, this is a set of size 2. Whereas in a hypergraph, right, the H set can include subsets of arbitrary sizes, right? Like for example, in relation to this same vertex set. So let's say this same vertex set we use, and let's say H here is denoted by V comma E, right? Here E could be made up of, let's say 1, 2, right? And it could also be made up of this edge over here. So you can see that here you have 3 elements. Is this okay? So because of the fact that this is not binary in nature, okay, this generic construct we will refer to as the hypergraph. Okay, so hypergraph is just like a graph. However, this E over here is a collection of non-empty subsets. We do not emphasize that these non-empty subsets should have size 2. If we impose that restriction, then that hypergraph will become a graph. Right. So now one can ask, what is the difference between a hypergraph and a simplicial complex? Well, the difference is that in this collection, we do not impose the necessity of this collection being non-empty, closed under this subset operation. Right. So we do not impose that condition. Right. So as soon as we impose that condition, a hypergraph will become a simplicial complex. Okay. So as I mentioned over here, as I mentioned before, E need not be closed under the subset operation. Hence, every simplicial complex is a hypergraph, but not vice versa. Is this okay? So a hypergraph is also a collection of subsets, but we do not require that this collection of subsets be closed under the subset operation. If you impose this additional condition, then a hypergraph will become a simplicial complex. Okay, so let us look at a bunch of examples, and then it will become clear, okay, what a graph is, what a hypergraph is, and what a simplicial complex is. Okay, so to begin with, let's look at this first example. Okay, in this the vertex set V is made up of these n vertices, right? So the vertices are labeled 1, 2, all the way up till n. Okay, so the simplest simplicial complex is the one that is given over here. Okay, so you take a look at the power set. So I will define what a power set is, and from this power set you remove the empty set, right? So let's recall what a power set is. Okay, so this notation means power set. Okay, so this is a collection of all possible subsets of V. Okay, so this notation over here refers to the collection of all possible subsets of V. I'm sure you all are aware that the empty set is a trivial subset of V. That's why this collection will also include the empty set, right? So you take this collection and remove the empty set, right? And then you will be left with this collection. Okay, so this collection will include sets which have just one element, right? So here there are n elements in this vertex set, right? So the first subset could be the set only containing the element 1. The next set could be the set containing only the element 2, and so on and so forth, right? So then you could look at the set which only consists of 2 elements, right? And so on and so forth, right? And eventually you include the set which has all the n elements over here. So I hope you agree that the power set minus the empty set will give you this collection over here, right? So in order to check whether this collection, so observe that we have a collection of subsets here. So in order to check whether this collection is a simplicial complex or not, we have to verify whether it's made up of non-empty sets. That's the first thing. And the second, whether it is closed under the subset operation or not, right? So can one of you help me figure out why this collection is closed under the subset operation? Can one of you tell me why this is closed under the subset operation? Can one of you help me figure out why is this closed under the subset operation?
All possible subsets are included. So
can you please raise your hand? I cannot see who is talking. Yeah, Deep, go ahead.
Yeah, all possible subsets are included in the delta except for the empty set. So that's why it's closed.
Yeah, so what I'm okay, maybe a more formal way would be, let us say you pick any set here, right? And you look at its subset. So let's say A is a subset and let's say this is non-empty, right? Now we know that S is a subset of V and consequently A must also be a subset of V. And in this collection, we have included all possible subsets of V and hence A must also belong to this collection over here. Right. So in that sense, you can see that indeed this collection over here is closed under the subset operation. And that's why this indeed is a simplicial complex. Is this okay? Now, you can also view this as a hypergraph, right? So I just have to write it separately, right? So for example, I will say the vertex set is 1, 2, blah, 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 all the way up till n. And the edge set is made up of 1, 2, 1, 3, right? All the way up till n minus 1 comma n and all the way up till 1, 2, blah, 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 up to n. Right. So this is just a different way of writing, but I hope you agree that both a hypergraph and a simplicial complex is a collection of subsets. Right. Here you have these different sets here and here you have different sets. Right. So if you sort of view this hypergraph as a combination of the vertex set and the edge set, you will see that again you have a collection of subsets, and in a simplicial complex also you have a collection of subsets, right? So you can think of this also as a simplicial complex and equivalently also as a hypergraph. Okay, this is just a different way of writing, but I hope you agree that both of this collection over here is a simplicial complex as well as a hypergraph. Okay, now often for convenience, okay, I don't want to write these curly braces several times. On one hand, it sort of complicates the discussion, and also it sort of is a bit inconvenient to write it often. Hence I will write this set in a sloppy fashion as 1. Right. So when I write 1, I actually mean this. Similarly, when I write 1, 2, I actually mean this set over here. Right. So let's look at another example and let's ask whether this collection over here, right? So this is delta, which is made up of these collection of sets, right? So I hope you agree that this is the set which has just one. This is the set which just has 2 elements, 1, 2. This just has the the 3 elements 1, 2, 3. So can one of you volunteer and help me figure out whether this collection of sets, whether it is a simplicial complex or not? What do you think? Is this a simplicial complex?
No.
Please raise your hand. Please raise your hand. I don't see. Yes, Harshil, go ahead.
3 is not present. It's a subset.
3 is not present. Very good. Right. So, for example, if you look at this set 1, 3, right? So 3, this is a subset of this. So this is non-empty, right? And we require that this collection should be closed under the subset operation, right? So this is not present, and consequently this is not a simplicial complex, right? In fact, this is not even a hypergraph, and I request you to see why this is not a hypergraph, right? So it's not a hypergraph because we need a vertex set, and the edge set should be a subset of the vertex set, right? So one cannot identify a vertex set for which the edge set can be viewed as a subset of that vertex set. Okay, so that's why this is not even a hypergraph. Is this clear? So I've given you some simple examples of what is a simplicial complex and what is not a simplicial complex. Okay, so if you have any questions in relation to the examples, this may be a good time to ask. Please go ahead. In relation to what are simplicial complexes and so on. Yes, Jacob, go ahead.
Sir, can you repeat that last point?
The last part was this is not a hypergraph. Is that what you want to know?
Yeah.
So what I said was, in a hypergraph, I hope you agree that we need a vertex set and we need a edge set, and the edge set, okay, should be a collection of subsets of V, right? So what would be the V that you will have over here? So maybe I'll tell you when would this collection become a hypergraph, right? So the collection here would become a hypergraph. Let's say if I added these three things, then you can think of 1, 2, 3 as the vertex set and these quantities over here as subsets of V. Then this would become a hypergraph. Do you agree? Jacob?
Not clear.
Not clear yet?
Yes.
So what I'm saying is that in a hypergraph, to define a hypergraph, I need two things. One is the vertex set V, and the other is the edge set. And the edge set should be a collection of non-empty subsets of V. So far, so good.
Yes.
Right. So I'm saying that if these things were not there and if delta was only the collection of these sets, right, it's not a hypergraph because I cannot define a vertex set, right? I cannot define a vertex set, right? So let's say 1 is a vertex or 2 is a vertex or something like that. And I can think of others as subsets of this edge set. Is this okay? That's why this cannot be naturally viewed as a hypergraph. Is this okay?
Okay.
Okay, on the other hand, if I added this 2 and 3 over here, then I can define this vertex set to be made up of this 1, 2 and 3 elements, right? And I can view this 1, 2 as a subset of 1, 2, 3. Do you agree?
Okay.
Right? And 1, 3 as a subset of this and 1, 2, 3 as also a subset of this, right? So in that sense, one can see that indeed one can then view this thing as a hypergraph. Is this okay? All right.
Yes, sir.
Okay. Okay, so now we will sort of study some. Yes, Deep, do you have a question?
Yeah, so the example that you gave beneath that hypergraph definition, so there it shouldn't be hypergraph, right? Because I don't have 1, 2, 3 separately. And I mean, I'm just a little confused here. You said I need 2 and 3 to be there and as
Yeah, so this
singleton
is a
sets.
hypergraph. Is this clear or no? You think this is not a hypergraph?
So it is a hypergraph, right? That's what I thought that you were saying it's not a hypergraph.
No, I'm saying this is a hypergraph. If this
okay.
2 and 3 is not there, then it is not a hypergraph. That is what I meant. Is this okay? Because if this 2 and 3 is not there, see, as I said, in a hypergraph, you need a vertex set V and you need a edge set, which is a collection of subsets of V. Is this okay?
Yeah.
Right. So if there is no 1, 2, 3, how like what would you think of 1, 2 as?
Okay.
Do you agree?
But why? I mean, from here I can just see that 1, 2, and 3 are the vertices, right? I am not getting what you're saying. How I can't the vertices.
So let me just write it. Yes, Neha, you had a point.
So I think previously you have mentioned that in bracket 1, 2, and 3, these are vertex set. So in bracket 1, 2, 3.
So how about I write it here? Okay, so let's say if I have these two descriptions. So let's say delta is 1, 1, 2, 1, 3, and 1, 2, 3. Is this okay? Right? I'm claiming that this collection over here cannot be viewed as a hypergraph, whereas, so maybe I'll put a cross over here, whereas this can be viewed as a hypergraph. This can be viewed as a hypergraph in the following way. I can define this vertex set over here and I can define this edge set to be 1, 2, 1, 3 and 1, 2, 3. Right? So you can indeed see that every element of E, right? So every element of E is a subset of V. Is this okay? Is this clear, Deep?
Yeah.
Okay. All right. Sneha, did you have a question or this is fine?
So this is fine.
Okay. All right. So now let us advance. Okay, so we will now look at some definitions related to a simplicial complex. Okay, so this will just be some hopefully 1 or 2 pages, and then this will be something that we will use throughout, hence it makes sense to discuss them for once and for all. Okay, so the one of the interesting things or important things with in relation to the subsets of delta. Okay, so henceforth we will refer to the elements of delta the subsets in delta or the elements in delta as faces. Okay, so this is something you may want to keep in mind. Henceforth, we will refer to the elements in delta or the subsets in delta, okay, as faces, right? So, so let's say sigma is some face in delta, right? The dimension of this face will be denoted by dim of sigma, and this will be equal to cardinality of sigma minus 1, right? So in this sense, I hope you agree that all the zero dimensional faces, right? So let's say delta is made up of 1, 2, 1, 2. Okay, so it is made up of 1, 2, 1, 2, right? So the zero dimensional faces. So this is a set. So let's say if I think of sigma to be 1, ideally I should write it this way, then the cardinality is 1 and the dimension of this sigma will be 0, right? So the zero dimensional faces are these guys. Okay, so these are zero dimensional faces, whereas this is one dimensional, right? And we will sort of use this set of words because these are more familiar. So the zero dimensional faces of delta, we will refer to them as vertices. Okay, the one dimensional faces, we will refer to them as the edges, right? And the two dimensional faces, we will refer to them as triangles, and the three dimensional faces, we will refer to as tetrahedrons. Okay, and for all the higher dimensional faces, we will sort of just call them either as faces, okay, or we will call them as simplices. Is this okay? Right? And in this spirit, one can now define the dimension of the whole simplicial complex. Well, the dimension of the whole simplicial complex is the maximum among all dimensions of the faces in it. Right? So what do I mean by that? So let's look at this simplicial complex. The dimension of this face is 0. The dimension of this face is 0. And the dimension of this face is 1. Right? So the dimension of delta will be 1 because the face with the largest dimension is this face and that is 1. Right? So similarly, let's say you had something like 1, 2, 3, 4, right? And then maybe you had 1, 2, 1, 3, 2, 3, right? And then you had 1, 2, 3. And let's say this was your simplicial complex, right? So you can verify that this is closed under the subset operation. Hence, it's a simplicial complex. And let's say this is delta, and the dimension of delta, which is the dimension of the whole simplicial complex, in this case, will turn out to be 2. And this 2 is because of this face over here, okay, which has 3 elements. Okay, so this set has 3 elements, and consequently, the dimension of this face is 3 minus 1, which is 2. Okay, so I hope the concept of a dimension of a face and the dimension of a simplicial complex is clear, right? And I claim that a simplicial complex of dimension at most 1 is a graph, right? A simplicial complex of dimension at most 1 is a graph, right? So this means that every face in this simplicial complex has dimension 0 or 1, right? Those are the only two possibilities. So which means that if you have delta, and let's say if you had something like this, right? So this is a graph. This is a graph because I can equivalently view this as this pair V comma E, where V is 1, 2, 3, and E is made up of the subset 1, 2. Right? So I can equivalently view it in this fashion. And my claim is that whenever you have a simplicial complex of dimension at most 1, it will necessarily be a graph, or equivalently, or it can also be equivalently viewed as a graph. Okay, so let me pause here for a second or two. If there are any questions in relation to dimension, or why it can be viewed as a graph and so on and so forth, this may be a good time to ask. Please go ahead. Do you have a question? All right. Okay. So the next concept, yes, Ankit, go ahead.
Hello, sir.
Yeah.
Yeah, if the dimension is 2, how it should not be viewed as a graph?
Because, right,
Yes.
see, let's say delta was something like this. So do you agree this is closed under the subset operation?
Yes,
Right?
sir.
I hope you agree that one can view this as a simplicial complex. Right? So my question is, how can you think of this as a graph? In order to be able to write this as a graph, you should be able to tell me what is the vertex set and what is the edge set. Do you agree?
Yes. Yes, sir.
And in a graph, one necessarily requires that all the elements in the edge set have size exactly 2.
Yes, sir.
Do you agree? So what do you do about this set over here?
I was thinking it as a triangle.
But so that's what I'm saying. See, in a graph, so I believe you're asking, what about such a graph?
Yes, sir.
Right? So you are saying, oh, this is a triangle. Why can I not view this as a, why can I not view this as, this graph over here? So let me give the representation. Okay. Or so the graph over here would be V comma E, right? And this V over here would be 1, 2, 3, and E over here would be made up of 1, 2, 1, 3, and 2, 3. Do you agree? These
Yes.
are the 3 edges. Now, if you look in this definition or this description of this simplicial complex, can you see we have this additional subset over here?
Yes, sir. Yes, sir.
Right? So you see 1, 2, 3 is there, 1, 2, 1, 3, 2, 3 is there, and then we have an additional relation. Right? So my claim is that if you view this as a graph, then you are sort of ignoring this additional information that has been given to you.
Okay. Okay.
Okay, so maybe I'll give you some, physical example, right? So let's say 1, 2, and 3 represent scientists at IISc. Is that okay? Right?
Okay.
So let's say I will put a relation between 2 of them if they have a paper.
Yes, sir.
Is this okay? I'll put a edge between 2 scientists if they have written a joint paper. So here, this information that we have tells us that 1 and 2 have a joint paper, 1 and 3 have a joint paper, 2 and 3 have a joint paper, right? But here we don't know if 1, 2, and 3 together have a joint paper.
Okay.
Do you agree? Right? This
Yes.
doesn't tell us that. Whereas here, I am explicitly telling you that 1, 2, and 3 also have a joint paper.
Okay. Okay, got it.
Does that help? Right?
Yes,
So we
yes,
are sort of, so this is what I said. In a graph, right, one sort of ignores these binary relations, one only incorporates binary relations. Is that okay? However,
Yes.
simplicial complex allows you to include higher order relations as well. So this is a higher order relation.
Okay, got it. Got it.
Okay. All right. Are
Thank
there
you.
any more questions in similar spirit? Okay, I don't see any raised hands, so maybe we can advance. Okay, so the next important concept that we will talk about is that of a kth skeleton of a simplicial complex. So let's say we have been given a simplicial complex delta, right? And we want to define its kth skeleton. Okay, so this skeleton can be defined for any integer k. However, it is of interest only when k is bigger than or equal to -1, right? So the kth skeleton of a simplicial complex delta will be denoted in the following way: delta raised to in circle k, right? So, or in round brackets k. So delta superscript round brackets k. So this notation over here refers to the kth skeleton of delta, and this is obtained from delta by removing all the faces of dimension greater than k, right? So the kth skeleton of a simplicial complex is the collection obtained by removing all faces of dimension greater than delta, right? So let's say this is our delta, right? So if this is our delta, and if I ask you what is delta 0, right? What is delta 0? So what would your answer be? Can one of you volunteer and tell me what should delta 0 be? Can one of you please volunteer? Please raise your hand. Yes, Deep.
Just 1, 2, 3.
1, 2, 3. Very good. So I have to throw away all faces of dimension greater than 0, right? So I have, I hope you agree that I have thrown away this, 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 and whatever remains is this. Similarly, I hope you agree that if I asked you to define what is delta 1, right, it will be 1, 2, 3, 1, 2, 1, 3, and 2, 3. Right? So I just need to throw away faces with dimension bigger than 1. Right? So this is a face with dimension 2, which is bigger than 1. So I throw it away. So this will be the one skeleton of this simplicial complex. Okay, so similarly, I can define delta 2, right? So this will be 1, 2, all the way up till 2, 3, and it will also include 1, 2, and 3. Is this okay? So basically, delta 2 will be delta. And I hope you agree that delta k in this particular case, for all k bigger than equal to 2, delta k will equal delta itself. Right? And one can similarly ask what is delta minus 1? Well, delta minus 1 will be empty. Right? Because there is no face. I mean, I have to throw away all faces with dimension strictly bigger than minus 1. Right? And consequently, this delta minus 1 will equal the empty set. All right. Okay, so this is how we define the kth skeleton. Right? Now I have here written another word. I have said that the kth skeleton is the subcomplex obtained by removing all the faces of dimension k. Right? My claim is that however you construct this kth skeleton, right? So the way you construct is you remove or throw away all faces of dimension greater than k. So you throw them all off. Whatever is remaining, my claim is that that will also be a simplicial complex. Right? Whatever remains, that will be a simplicial complex. Why would it be a simplicial complex? Because it will be closed under the subset operation. Okay, so this is closed under the subset operation. This is closed under the subset operation. Hence, these objects themselves are simplicial complexes. Hence, and since these are subsets of delta, right, we will refer to these objects as subcomplexes. So the formal definition of the kth skeleton is the subcomplex obtained by removing all faces of dimension greater than k. All right. And now here is a quick remark. Okay. The one skeleton of a simplicial complex is always a graph. Right. So here again, what we are doing is whatever is the simplicial complex. Okay. We are ignoring faces of dimension 2 and above. Right. So in other words, we are ignoring all higher order relations and we are only focusing on relations concerning dimension 0 and dimension 1. Okay, so whatever we get back, since that itself is a simplicial complex, right? One can say that that can also be equivalently viewed as a graph. Okay, so yes, Jacob, go ahead.
Sir, delta raised to minus 1 is empty, right? But
yes.
A simplicial complex needs to be non-empty.
Simplicial complex need not be non-empty. It should be a collection of non-empty sets, right? Okay. So this is like this is a special or a a special simplicial complex. Is this okay? The empty simplicial complex, I agree, it sort of is a bit tricky, but we will sort of think of this as a simplicial complex that has no sets. Is this okay?
Yes, sir.
Okay. All right. Okay, so I hope this is clear what a kth skeleton of a simplicial complex mean, and I hope you agree that whatever be the simplicial complex, its 1th skeleton, okay, can always be viewed as a graph, right? And here is a disclaimer. Okay, throughout this course, we will only focus on simplicial complexes with finite vertices, right? So all the faces can be viewed as subset of this vertex set. Right. So throughout this course, we will only focus on simplicial complexes whose faces can be viewed as a subset of a given vertex set. And in that vertex set, we will always assume that we only have finitely many vertices. Okay, in general, that is not required. You can also look at simplicial complexes on infinitely many vertices and so on. Right. However, this is an introductory course on computational topology, and hence our focus will be on simplicial complexes with finite vertices. And consequently, all our simplicial complexes will be finite dimensional, right? So here is a quick question. Let's say V is 1, 2, blah, blah, blah. And let's say delta is collection of subsets of some subsets. We did not include all subsets, some subsets of V, right? And let's say that is closed under the subset operation, right? So we look at some subsets of V and we will ensure that this collection is closed under the subset operation. Can one of you tell me what can be the maximum dimension of delta? Can one of you tell me what can be the maximum dimension of delta? Yes, Dhurjati, can you go ahead?
n-1.
Very good. N-1. Can you explain why?
Because there are n elements and the dimension is defined as n number of elements minus 1.
Yeah, so maybe you want to say that the largest set that can belong to this collection is the set 1, 2, all the way up till n. Is this okay? And this is the largest set that can belong to delta, and this dimension is n-1. Hence, the dimension of delta can at most be n-1. Very good. Okay, so this is basically a proof for this statement that whenever you look at simplicial complexes over finite vertex set, then the simplicial complex will be finite dimensional. All right. Okay. Okay, so in the remaining 20 or so minutes, our focus will be on this concept that will be called as a geometric realization of a simplicial complex. Okay, so a question that may naturally arise in your mind is, okay, what do you mean by geometric realization, right? By geometric realization, loosely, so first I'm giving you an intuitive definition and then we will look at the formal definition. Okay, by geometric realization, loosely, we mean how to draw or imagine a simplicial complex, right? So far, I'm just writing it as a set, right? So I've written this, right? So I wrote something like this, let's say, right? So I just wrote it like this. So you may ask, can I also draw a simplicial complex? So the answer is yes, you can draw it. However, we want that you follow certain rules. We don't want you to draw it in an arbitrary fashion, right? We want you to draw or follow certain rules while you draw or imagine a simplicial complex. And when you follow these rules, whatever the drawing that you end up with is what will be your geometric realization of a simplicial complex, right? So this was the loose definition. Formally, what do we mean by a geometric realization? Well, formally, a geometric realization is a way to associate a topological space to a simplicial complex, right? Formally, a geometric realization is a way to associate a topological space to a simplicial complex. Okay, so the formal description of a geometric realization involves some technical concept that that of a topological space, right? So what is a topological space? I have defined below, but nevertheless, let me make a remark. While there is no unique way to construct this topological space, however you construct this topological space, however, all these spaces will be homeomorphic to each other, right? So what does geometric realization mean? Whenever you are given a simplicial complex, you sort of cook up a topological space, right? So what is a topological space? I'll explain. Think of this as just a space, right? While there is no unique way to come up with this space, all the spaces that you do come up with, or all possible spaces that you do come up with, by ensuring that you follow all the rules, one can show that the resultant spaces will all be homeomorphic to each other, right? While there is no unique way, nevertheless, whatever space you come up with, okay, they all will be homeomorphic to each other. Okay, so that is something you may want to keep in mind, right? So now let me describe a formal definition of what do I mean by a topological space, right? So topological space, again, like graphs, homology groups, simplicial complexes, vector spaces, and so on. This is an abstract entity, right? So what is a topological space? Well, it's a pair, right? So whenever I say a topological space, you have to imagine a pair. The first element in the pair is X, and this is some set, right? So first element in this tuple is a set, okay, and this we will denote it as X. And the second element over here, we will denote it by tau. This is a collection of subsets of X, right? So again, it's a collection of subsets of X. However, here we require that this collection satisfy a bunch of axioms, which is different to the kind of axioms that we saw, let's say, in the context of a simplicial complex or something else, right? We require that this collection satisfy a different set of axioms, right? Or different set of properties. So what are these different properties? The first property is that in this collection, we should have the empty set. Similarly, in this collection, we should have the whole set, right? Whatever is this X should be there in the collection. This is the first requirement. The second requirement is that this collection that we have should be closed under finite intersections. So what do I mean by that? Let's say this collection has k many elements, right? A1, A2, A3, all the way up till AK. Okay, so this k many elements lie in tau. So if you look at the intersection of these sets, okay, A1, A2, all the way up till AK, if you look at their intersection, we require that this collection also be in tau, right? So that's what I mean by tau being closed under finite intersections, which means that you consider finitely many elements of tau. Notice that tau is a collection of sets. So each of this is a set. You look at these finitely many sets and take their intersection, right? And whatever is the set that is an outcome of this intersection, that set should also lie in tau. Is this okay? So that's what I mean by closed under finite intersections, right? And the last thing we require is that this collection tau over here, okay, this should be closed under arbitrary unions. Okay, so this should be closed under arbitrary union. So what do I mean by that? So again, recall tau is a collection of sets, and let's say we have a bunch of sets in this collection, and let's index it by alpha, where alpha lies in I, right? So one can ask, what's the difference between this collection of sets and this collection of sets over here? Well, the difference is that here at any given time we are only allowed to consider finitely many elements in this collection, right? Here on the other hand, we can also consider uncountably many elements, right? Here we are only allowed to consider finitely many. Here on the other hand, we are allowed to consider uncountably many sets as well, right? So that's why here we say we require that the property be closed under arbitrary unions, not just finite unions, right? So let A alpha belong to tau for alpha in some index set. So this is some index set over here. So this is some index set, right? And let's say A alpha lies in tau for all alpha in I. Then closed under arbitrary unions means that, okay, closed under arbitrary union means that the arbitrary union of these A alphas. So notice that I'm taking the union of A alpha for alpha in I. So this union must lie in tau. Is this okay? So if these three properties are satisfied by this collection tau, right, we will say that this pair over here is a topological space. Okay, so let me give an example. Of course, the example that I'll give you is going to be very trivial, but nevertheless, to begin with, this is good enough, right? So let's say X is a set which is made up of these elements, two elements, and let's say I give you, this collection, right? So let's say I give you this collection over here, right? So again, this has to be interpreted as this set, and this has to be interpreted as this set, right? So the first question one can ask is tau, does X comma tau define a topological space? Well, the answer is no. This is because the empty set does not belong to tau, and also X does not belong to tau. Right, so these two properties, I mean, these two sets are not present in the collection. Hence, this condition over here is violated. So let's modify the definition of tau. So let's say tau includes the empty set 1, 2, and 1, 2. Right, so this is the collection. Right, so now my question is X and is X this set over here and this collection of subsets over here, is this a topological space? Well, the answer is that yes, it is a topological space, because you can see that this collection will satisfy all these three axioms, right? So let's quickly verify some of them. So we require that the empty set and the whole set lie in the collection. So that is indeed true. So you can see that empty set and the whole set lies in the collection. We require that it be closed under finite intersections. So you give me a bunch of sets from this collection. So let's say you give me 1 and 2, right? So this is 1 So this is 1 and let's say this is 2. And if you look at the intersection, so the intersection, I hope you agree, is empty, and clearly this empty set lies over here, right? And similarly, let's say you took 1 and let's say 1 comma 2, right? The intersection is 1 and this one indeed lies over here. So you can see that in this way, every whatever be your finite collection of sets in this from this collection, if you take their intersection, you will see that it always lies in tau, right? And the last property here again can be trivially verified, because although we require that this property be closed under arbitrary unions, you can see that there are only finitely many sets here, right? So even if you take arbitrary unions, okay, you will only end up with finite unions, right? So because of that reason, you will see that this property is also true, right? Now let me so consequently this x okay, this space x and this tau over here is indeed together, they indeed together form a topological space, right? So now let me give you a non-trivial example. So let's say x is R, right? And let's say tau is the collection of all open sets of R, right? So I won't have time to define what's an open set and so on. And also it's not a key thing that we will be required to study in this course. However, those who are interested, okay, they can either look up on Wikipedia or something else, right? So if you look at the collection of all open subsets of R, right, then this collection together with this space X can indeed be viewed as a topological space. Okay, and this collection tau will include intervals, let's say 0, 1, it will include 1, 100, or maybe it will include -5, 75. So all these intervals will be present. Okay, so of course the closed intervals will not be present in this collection, because the closed interval is not an open set. In particular, there are issues at the boundary. Okay, but then you could have asked, does this collection only include these open intervals? Well, the answer is no. It can also include unions of intervals like 0, 1 union 1, like 5, 10, right? So this is a union of intervals. So by itself, it's not an interval, right? But it's an union of interval, and this will also lie in this collection, right? So in fact, it can include arbitrary union and countable unions and all possible unions you can have, and that union will also be present in this collection over here. Is this okay? So this was a slight digression, and I hope I gave you like a very loose description of what do I mean by a topological space. So let me pause here for a second or two. Okay, if you have any questions in relation to the definition of a topological space, this may be a good time to ask. Do you have any questions? Do you have any questions with regards to a topological space? Okay, so I don't see any raised hands. Perhaps this is the first time you are encountering this notion of a topological space. It's fine. Okay, you can think about it. And if you have any questions, you can ask them either during the office hours right after the class, or you can ask me in the next class, or alternatively, you can post on Teams as well. All right. Okay, so with this, we can advance. Okay, so why did I define a topological space? Well, the reason is that because we want to define a geometric realization of a simplicial complex. Okay, and a geometric realization of a simplicial complex means that to every simplicial complex, you attach a topological space, right? So what is this topological space? In order to define that, I have to give you a set and the collection of open sets in that set over there, right? Okay. Okay, so maybe I'll just add one remark over here, right? So one of you may ask, oh, what is this topological space? Why do we need it? And so on and so forth, right? So this is needed because often in practice, right? No, this is not just a mathematical entity. This is something that is useful in practice as well, right? So let's say you had a bunch of so let's say you had a collection of all possible 256 cross 256 sized images, right? So let's say you had all possible 256 cross 256 images. right? So I hope you agree that if all these images are monochrome images, that is it will only be made up of shades of black, right? So if you only include different shades of black for every pixel in this image, right? So then I hope you agree that each image can be represented as a 256 cross 256 matrix. And let's say you have a collection of all possible such images, right? So all possible images meaning all possible 256 cross 256 matrices, right? Now this is a collection of elements, right? So the collection can be viewed as a space. Now if you wanted to define a function over this space, and if you wanted to ask when would this function be continuous, right? So in order to answer such questions, one would have to first define a collection of sets, okay, which satisfy the three properties that we mentioned in the definition of a topological spaces, right? And all the sets in this collection would be referred to as open sets. Okay, so as I mentioned, okay, maybe I have not written it here, but all sets in tau will be called open sets, right? So you look at this example of all these 256 cross 256 matrices, right? Then you identify some collection of sets, and those sets you will define to be open. Why do you define to be, why do you, how do you choose which sets you will call it as open? Well, it will depend on which functions continuity you are interested in studying. Okay, so it will depend on those kind of questions, right? And accordingly, you will define that collection, right? So the answer is, why are these topological spaces useful? Well, they are useful when you want to define a continuity of functions, right? If you just had a set, right? Let's say there was a set X and you defined a function from X to Y, right? One cannot talk about the continuity of F. In order to be able to talk about continuity of F, you need that X and Y both be topological spaces. Okay, so I mean, this is just a short remark. Even if you sort of don't understand it, it's fine. But this is just a remark so that you can keep in mind, why do we require this concept of a topological space? All right. Okay, so let's now move on to discussing this geometric realization. Okay, so let's see what we have. Right, we have been given this simplicial complex delta. Okay, so as I mentioned some time back, okay, I'll be sloppy, and instead of calling this as an abstract simplicial complex, I'll simply call it as a complex, and I will denote it by this notation delta. Right, and what is our goal now? Our goal is to define a geometric realization. Loosely, we want to know how can one draw a simplicial complex. Okay, that's what we want to do. But formally, we want to associate a topological space. Right? So how do we do that? So let's say we have been given this simplicial complex delta. We first identify the vertex set of delta. Right? We first identify the vertex set of delta. This is the collection of all zero-dimensional faces in delta. Okay, V is the vertex set. This is the collection of all zero-dimensional faces in delta, or sets with cardinality 1. Okay, once we have this vertex set V, we identify a function, right? We identify a function whose domain is this vertex set, and the codomain is Rn for some n, right? So this is n for some n, right? So now one can ask how to choose n and so on and so forth. It will become clear soon. How should you choose n? Right, it will become clear soon. How should you choose n? Right, so what does this function do? It takes as input one vertex, which I've written here as little v, in this set of vertices, and assigns to this vertex a vector in Rn. Right, so every vertex is assigned a vector in Rn. Right, so the output of v under f, or the output of f for v would be this vector over here, and this is an element in Rn, so it will have n coordinates. Right, now my claim is that for from this f, for every d phase sigma, this f over here induces another function. Let me repeat. You first define this function f, right? So this function takes as input this vertex set, this vertex v, and spits out a vector in Rn. The claim is that for every d phase sigma, right? So every d phase sigma. So since it's a okay, I should elaborate. When I say d phase, I mean a d-dimensional phase, right? I should have been careful here. So when I write d phase, I mean a phase with dimension d, right? Since it has dimension d, the phase itself will have d+1 vertices, and for convenience, let me write it as v0 to vd, right? So the claim is that you give me any d phase in delta, then this f over here induces another function, right? And what is that function? Well, the function, I will denote it as f subscript sigma, right? And its domain is xd. I will soon tell you what this xd is, and the output is rn, right? So whatever is the output over here, it is the same output, right? So again, let me repeat. You first define a function f. For every d phase sigma, this function f over here induces another function. Induces means it sort of leads or helps in defining in a natural fashion another function f sigma. The domain of this function is xd, which I will soon define, and the output of this function is rn, right? So what do I mean by xd? Okay, so the xd over here is what we will call as the standard d complex or the convex hull of the points 1 0 0 all the way up till 0 0 1 in rd+1. Okay, so I will elaborate what do I mean by that. Okay, but the first thing is this d over here is the same as the dimension of the face. That's the key thing to note. Whatever is the dimension of your face, that will be the d over here, right? So let me illustrate what do I mean by xd, right? So let's first look at x0, right? X0. Okay, this is x0 is the convex hull of a vector 1 in R, right? So this is a vector with only one coordinate. Okay, so I can trivially write this as 1, right? And I am looking at the convex hull of just one point in R. So I hope you agree that since I have only one point, its convex hull will be that point itself, right? So this is the standard 0 simplex. Okay, so now let us look at the standard 1 simplex, or what is x1, right? So for x1, we have to look at these vertices in R2, right? So these vectors in R2, what will be the corresponding things? Well, it will be 1 0 and 0 1. Okay, so here is a pictorial representation. Okay, here is the x-axis. Okay, so this is the x-axis, this is the y-axis, and this is the R2 plane, right? To identify these vectors over here. So this is 1 0 and this is 0 1, right? So you see this. So I have given you these 2 points over here, right? And the question now is to take their convex hull. So you have been given this point over here, you have been given this point over here, and I hope you agree that this line connecting the two is basically the convex hull between these two vertices. Is this okay? So this line segment over here, sorry, this line segment over here is what is x1, right? So if I ask you what is the standard 2 simplex, well, the answer is that you look at the vertices 1 0 0 0 1 0 and 0 0 1 and look at the convex hull. Well, the convex hull will be the triangle that sort of connects these three vertices over here. Okay, so I hope it's clear what x0 is, what x1 is, and what x2 is. Okay, I realize that I'm at the end of the class, so maybe this is a good point to stop, and from in the next class maybe we can begin understanding how this f sigma function is defined. Okay, so in today's class we finished understanding what xd is, but we haven't exactly defined what is this induced function over here. Okay, so let me stop recording, but I'll be available for a few more minutes and you can ask me questions.